This is Module 13, Section 7.6, Part 2, about problem solving with rational equations. First, we're going to look at how to solve problems about work. So a work problem involves a task to be completed, the time required to complete the task, and also the rate at which the work is done. Work problems often involve rational expressions because we consider the task to be completed as one whole unit divided into several equal parts. If a whole task can be completed in t hours, for example, then we use the reciprocal of t to find the amount of work done in 1 hour, which is the rate. Here's an example. George can install new wiring for a computer in 3 hours. How much of the job can he complete in 1 hour? This is where we're going to use the reciprocal of the time it takes him to complete the whole task. So the time to complete the whole task is 3 hours. So if we want to know how much of the job he can complete in 1 hour, then we're going to use the reciprocal of 3 to give us the fraction of the job that he can complete in 1 hour. So the reciprocal of 3 is 1/3, and that means he could complete 1/3 of the task in 1 hour. Now, one convenient way to solve work problems is to use tables. So let's look at how we would set up a table to solve a work problem. First of all, if we're talking about several different workers, we're going to use one row of the table for each different worker. We'll also have an extra row at the bottom of the table to show what happens when all of the workers work together. For the columns of the table, we'll use one for the total time needed to complete the whole task, another column for the rate of work, in other words, how much of the job a worker can get done in 1 hour or 1 minute, whatever the time units are. That's where we'll use the reciprocal like we did on the last slide. So here's a table. If we had a couple of workers here, we could put in our first worker in the first row, second worker in the second row, and then for our third row, we'd have them working together. Now for the columns, this first one would be total time for the whole task. And our second column would be the rate of the work. So this would just be the reciprocal of total time. Now, in order to fill out the rest of the cells in this table, first we want to read through the problem and determine what quantity or quantities the problem is actually asking for. And in most cases, it works best to use a variable to represent that quantity, the one that the problem is asking for. Sometimes the problem will ask for 2 quantities, and in that case, we would pick one of them to let our variable stand for. And finally, after we take all the information in the problem and complete the table, then we would want to reread the problem to find any comparisons that are made between times or rates. And we'll use these comparisons and the information from the table to write an equation. Here's an example. Starting again with George installing new wiring for a computer in 3 hours, then we also have the information that it takes Pete 4 hours to do the same job. So how long would it take if they worked together? So let's fill out our table. We have George as one of our workers, Pete is another one, and we're going to use our third row for them working together. Then remember, this column is going to be the total time, and this column is going to be the rate or the reciprocal of total time. So that's going to equal our rate. Now let's put in the information that we have. We know it takes George 3 hours to complete the whole job, so we'll put that down as our total time here. It takes Pete 4 hours. The question is, how long would it take if they worked together? Since the problem is asking for how long it would take if they worked together, let's make that our variable. So the total time it would take them if they were working together would be what would go in this cell right here. So let's make that X. So the answer to this question is going to be X hours. Now we can fill in the last column of our table just by using reciprocals. The reciprocal of 3 hours is 1/3. The reciprocal of 4 hours, 4 is 1/4. And the reciprocal of X is 1/X. Now that we've got our table filled in, we need to think about any other comparisons or relationships between these numbers from the original problem. There isn't anything in here that says that 2 rates or times are the same, so the only other thing that we know is that if we take the rate that George works and the rate that Pete works and add those together, we should get the rate that they work together. Let's write this down here. George's rate plus Pete's rate should equal their rate working together. And that means since we have those 3 rates here, we can write an equation using this last column of the table. 1/3, which is George's rate, plus 1/4, which is Pete's rate, should equal their rate working together. If we look in our table, that was 1/X. Now we have an equation and we can solve it for X and get the answer to our question. So to solve this, we can multiply through by the LCD. First, we find the LCD of 1/3, 1/4, and 1/X, and that's going to be just 3 times 4 times X, or 12X. We're going to multiply each rational expression by that. So we're going to have 12X times 1/3 plus 12X times 1/4 is equal to 12X times 1/X. And now if we cancel, we can cancel the 12 and the 3 and get a 4 up here, the 12 and the 4 and get a 3 up here, and we can cancel the X's over here so that we have a 12. So that gives us 4X plus 3X is equal to 12. So then we have 7X is equal to 12. If we want to solve for X, we divide both sides by 7. So that gives us X is equal to 12/7. Since we started out with the rational equation, we should take our potential solution and put it back in our original equation, at least to make sure that we don't get a 0 in the denominator. Let's check this. If we put 12/7 in here for X, that's definitely not going to give us a 0 in the denominator anywhere. So if we wanted to check the arithmetic, we could go ahead and do this, but it looks like this is okay as far as not making any denominator 0. So that would mean that our solution would be X is equal to 12/7, and our units for X were hours. So that would mean it would take them 12/7 hours to complete the job together. Here's another example. We have a graduate student that can grade a set of tests in 9 hours. Working with his professor, in other words, when they're working together, it takes only 3 3/5 hours to grade the set of tests. How long would it take their professor if she graded the papers alone? So first, reading through the problem, what the problem is asking for is how long it would take the professor to grade the set of tests by herself. So we're going to let this equal X. So let's write this out down here. We're going to say let X equal the time for the professor to grade the tests. All right, so now setting up our table, we have our grad student, our professor, and our last row is for the 2 of them working together. And again, our columns are total time here and the rate here, which is the reciprocal. So we know our grad student takes 9 hours. Our professor, we call the time that she takes to grade the test X. So that would be X hours. And we know how long it takes them together. It takes them 3 3/5 hours. Now to make this easier, let's convert this to an improper fraction. So 3 times 5 is 15 plus 3 is 18. So that's 18/5. Now to do the reciprocal of each one of these, the reciprocal of 9 is 1 over 9. The reciprocal of x is 1 over x. And the reciprocal of 18/5, if we already have a fraction, we're just flipping over the fraction, so that would be 5/18. And we have the same situation that we did in the last problem. In other words, these two rates together should add up to this. These two rates together should add up to this one. So our equation would be 1/9 plus 1 over x is equal to 5 over 18. So we're going to solve this by finding the LCD. Since we have 9 and 18, 18 is 2 times 9, so we have a 2 and a 9 and an x as part of our LCD. So that would give us 18x. Now we're going to multiply each rational expression by that 18x. And then we can do some canceling. So here we can cancel the 18 with the 9 and have a 2 left. Here we can cancel the x's. And here we can cancel the 18s. So that gives us 2x plus 18 is equal to, and here we have x and 5, so let's write that as 5x. Now if we subtract 2x from both sides, that gives us 18 is equal to 3x. Then if we divide both sides by 3, then that gives us 6 equals x. Now let's go back and check this in our original equation. We would have 1/9 plus 1 over 6 is equal to 5 over 18. And we can see right now that none of the denominators are 0. Let's complete the check just to make sure we haven't made any arithmetic mistakes. So we could do this by getting a common denominator between 9 and 6, which would be 18. So we take 1/9 times 2 over 2. We take 1/6 times 3 over 3 to get our denominators of 18. That would give us 2/18 plus 3/18. And if we add those together, we're going to get 5/18. So that checks. That means that our x equals 6 is our solution. It would take the professor 6 hours to grade the test alone. Okay, let's look at one more example of this kind of problem. In this one, we have Marcus who assembles crafts in his home, and it takes him 2 hours to complete a package of napkin holders. His daughter takes 8 hours to do a package, and the question is how long it would take them if they worked together. So what the problem is asking for is the total amount of time for them to complete the task working together. So let's make that our x. So let's say let x equal total time for them working together. Now let's fill out our table. So we have Marcus and his daughter, and then our third row for the two of them working together. And this column is total time, and this one is rate, which is the reciprocal. So the total time for Marcus to complete the task is 2 hours. The total time for his daughter to complete the task is 8 hours. And our question is how long it would take them if they work together. So X hours is the total time for them to complete it working together. Now we do our reciprocals, so we have 1/2, 1/8, and 1 over X. And again, we can add the two rates here. And those two together should equal the rate of them working together. So that gives us our equation. We're taking the 1/2 and the 1/8 and adding those together, and we should get the 1 over X. Now we just have a rational equation to solve. So our LCD, if we think about 8, that's the same as 2 cubed. So our factors, we've got 2, and the highest power of that is 2 cubed, and we've got X. So our LCD is going to be 2 cubed times X, or 8X. We're taking 8X times each one of our rational expressions. So 8X times 1/2, plus 8X times 1/8 is equal to 8X times 1 over X. Then we're canceling. So if we cancel a 2 from here, we have a 4. If we cancel here, we can cancel both of the 8's. And here we can cancel both of the X's. What we have left from here is 4X. What we have left here is just X. And what we have left here is 8. So if we combine these two terms, we have 5X is equal to 8. Then we're dividing both sides by 5. And that gives us X is equal to 8/5. Now let's do a check. Remember, with these, we're going back to the original equation before we use the LCD. And here we're putting in 8/5 in place of X. Now, if we were going to add these two fractions on the left side, we would want a common denominator, and our LCD between these two would just be 8. So let's rewrite this first fraction so that it has a denominator of 8. That means we may need to multiply the top and the bottom by 4. The second one doesn't need to change since it already has our denominator. So now we have 4/8 plus 1/8, and that's going to give us 5/8. And on this side, if we're dividing by 8/5, we can invert and multiply. So we're going to take the 8/5 and flip it over. And that gives us 5/8, which is what we come out with down here. So that means that our solution checks, and we can say it would take them 8/5 hours, or we could write this as a mixed number. We could make that 1 3/5 hours working together. Now we're going to look at a different type of problem called a motion problem. These problems involve distances, rates, and times. And there's a specific formula that we're going to use to solve these kind of problems. And that is that distance equals rate times time. A shorter way to write this is just to use d for distance, r for rate, and t for time. So we get d is equal to rt. So here are a couple of examples just of using this formula. We have a boat that travels at a rate of 5 miles per hour for x hours. So our 5 miles per hour is our rate, or our r, and x hours, that's a time amount, so this would be our time. And we want an expression giving the total distance traveled by the boat. So we're trying to find the distance, and we know that distance is equal to rate times time. So we have our rate of 5 miles per hour times our time, which is X hours. And if we multiply those two together, we get 5x. And if we think about this miles per hour, we could write as miles over hours. Our hours would cancel out and we would just get miles. So this would be 5x and the unit would actually be miles. Now another one, a cyclist bikes at a constant speed of 12 miles per hour for 15 miles. How long will this take him? So when we talk about a speed, that's the same as a rate. So this is a rate. And if we say he travels for 15 miles, that's actually a distance. And when it's asking how long this will take him, that's asking for the time. So we can still use this formula. It's just that this time we're going to solve for the t, since we have both the distance and the rate. So if we put the distance in for d on the left side, our speed or our rate of 12 miles per hour for our rate, and that's times the time. Now to solve for t, we have to divide both sides by 12. So we're going to have our 15 miles over here divided by the 12 miles per hour. And notice when we do this on the bottom with these two units, this is just like we're dividing by a fraction. So we could invert and multiply, and we'd end up with hours over miles on the top, and the miles would actually cancel out. So what this ends up being is 15 divided by 12, and our unit ends up being hours. And we could reduce this. This would actually reduce down to 5/4 of an hour. For motion problems, it also works pretty well to use tables. We're going to use one row of the table for each different part of a trip. And then our columns are going to be the distance, the rate, and the time. So if we had a trip, say we had the first leg of the trip and the second leg of the trip, and then up here we would have our distances, then rate, and then time. If it helps you, you can even write an equals in here so that you have your formula, and put a multiplication in between the rate and the time so that you remember what that formula is. Just like we did with work problems, we're going to want to read through the problem and then figure out what quantity or quantities the problem is asking for, and we'll usually use a variable to represent this quantity in our table. And if there are two quantities that the problem is asking for, we'll pick one or the other of them. Then we'll use a form of the distance equals rate times time formula to complete the table. In the example on the last slide, we took that formula and solved for time. So we might do something like that. If we want to solve for the time, we might say d over r equals t, or we could solve this for r, the rate, and that would be d over t is equal to r. So that's what we mean by one of these forms. And again, after we complete the table, then we'll reread the problem, find any comparisons that are given between distances, rates, or times, and we'll use these comparisons and the information in our table to write an equation. Here's a problem for us to solve. So Olga walks 2 miles at one rate for the first half of her workout. In the second half of her workout, she spends the same amount of time walking 3 miles at a rate that is 2 miles per hour faster. And we're supposed to find both of Olga's rates. The problem is actually asking for two different quantities. So we'll have to pick one or the other of them to be our variable. So let's just say that x is her rate for the first half. of the workout. Because we've got one rate for the first half, one rate for the second half. We just have to pick one or the other of them to be our variable. Now let's fill in our table. So we have the first half of the workout, the second half of the workout, and we have distance, rate, and time for our three columns. So in the first half, it tells us that she walked a total of 2 miles. And the rate for the first half is actually our variable, so we'll put x in there. And it doesn't tell us what the time is for that first half. Then for the second half of the workout, she walks 3 miles, so that's her distance, at a rate that is 2 miles per hour faster. So here's a comparison between the two rates. This rate for the second half is 2 miles per hour more than the rate for the first half. So we can actually put an expression in here for this rate. This would be x plus 2. This makes it 2 miles an hour more than the rate for the first half of the workout. And again, we don't have a time given us for how long she took in the second half of the workout. So this is all we can fill in for now. Let's go back to the problem and see if there's any other information that we haven't used yet. And one thing it does tell us is that she spends the same amount of time in both halves of the workout. So that means that these two times are equal. So that's something we can use. We still don't have anything else that we can use to fill in these two boxes though. So what we're going to do is use our formula, and we're going to solve for time. If we just take our formula and solve it for t, we have time is equal to distance over rate. So we can use that to fill in our two boxes. For this first row, distance over rate would be 2 over x. For the second one, it would be 3 over the quantity x plus 2. So that's another way to fill in boxes that you couldn't fill in any other way in the problem. And now we know that these two times are supposed to be equal, so that actually gives us an equation. We just take those two expressions, we know they have to be equal to each other, so we just set them equal to each other. And notice what we have here, we only have one rational expression on each side of the equation, so we can use cross multiplication here. So we can take the 2 times the x plus 2, set that equal to the x times the 3, or 3x. Now we can distribute the 2, so we get 2x plus 4 is equal to 3x. So now if we subtract 2x from both sides, that gives us 4 on the left side and just x on the right side. Now let's go back and check the solution in our original equation. So we're going back to our equation with the rational expressions and substituting 4 for x. So if we have 2/4 on this side, we could reduce that down by canceling out 2's. That would reduce down to 1/2. And on the right side, we have 3 over 6, which also reduces down to 1/2. So that checks. Now we were supposed to find both of Olga's rates. So the x that we got is the rate for the first half of the workout. So that's going to be 4, and our units were miles and hours. So this is going to be miles per hour. And then the rate for the second half we can use our table because we had x for the rate of the first half, x plus 2 for the second half. So all we have to do is take the rate for the first half and add 2, and that gives us 6 miles per hour for the rate in the second half. Here's another motion problem. In this one we have a cyclist who bikes at a constant speed for 18 miles. On his return trip he travels at the same speed but goes by a different route, which is 23 miles long. If the return trip takes 1 hour longer, find the speed. So in this one, what the question is asking for is the speed, and notice that he goes the same speed in both parts of the trip. So let's just call this x, and remember speed is the same as a rate, so that's going to be a rate. And so we've got his trip going is the first part and returning. And we've got our distance, rate, and time up here. So the distance when he went was 18 miles. On his return trip it was 23 miles. And he goes at a constant speed, and it's the same for both, and the speed was our x. So we can actually put x in for both of these rates, and we don't have actual time values to put in these boxes. So let's try what we did on the last problem, and that is solving our distance equals rate times time formula for t. We get t equals d over r. That means we can divide the distance by the rate and get the time. So for this first time we'd have 18 over x. For the second one we'd have 23 over x. Now let's go back to the problem and find any more comparisons that were made. We know he traveled at the same speed in both parts of the trip. We already have that in the table. The only other thing that we haven't used is that the return trip takes 1 hour longer than the trip going. So that means that the time in this part is 1 hour longer, or 1 hour more, than the time in the first part. We could translate this into an equation. We could say the time for the second part, or the return trip, is 1 more than the time for the trip going. So the time for the trip going was 18 over x. 1 more than that would be that plus 1. And there's our equation. So looking at this, our LCD would be just x. So we're going to multiply each rational expression on both sides by x. We have x times 23 over x equals x times 18 over x plus x times 1. It's easy to forget this part of multiplying the x times whole numbers, but you have to do that part too. Now we can cancel out the x's here, and we can cancel out the x's here. So we have 23 is equal to 18 plus x. Then if we subtract 18 from both sides, we end up with x is equal to 5. Let's check this in our original equation. So we would have 23 over 5 is equal to 18 over 5 plus 1. On this right side, if we wanted to add these two together, we could rewrite the 1 so that it had a denominator of 5. So we would multiply it by 5 over 5. So that gives us 18 fifths plus 5 fifths. We could add those together, and that would equal 23 fifths. So that checks. And since the x was our speed, which is what the problem was asking for, then we can answer the problem by saying the speed was 5. And we do want to put the units in here, and notice that our units for the distance is miles, and the time units were hours, so this would be miles per hour. Let's do one more motion problem. In this one we have a boat that can travel 22 miles upstream in the same amount of time that it can travel 42 miles downstream. the speed of the current is 5 miles per hour. And we want to find the speed of the boat in still water. In these kind of problems where you have either a boat with the current or an airplane with the wind, you have to think about the directions. So let's draw a little picture here to help us. If this is our river, and let's say that the current is flowing this way. So that would mean that this direction would be downstream. And if we were going this direction, that would be upstream against the current. So if the boat is going downstream, the boat's speed is going to be added to the current. So downstream we have the boat's speed plus the speed of the current. But if the boat is going upstream, then since it's going the opposite direction of the current, then we would have the boat's speed minus the speed of the current. It works the same way with problems where you have an airplane and the wind. If the airplane is going with the wind, then you add the speeds together. If it's going against the wind, then you subtract the speed of the wind from the speed of the airplane. Okay, so our two different parts of the trip are upstream and downstream, and we have our distance, rate, and time. So on the upstream part, the distance was 22 miles. In the downstream part, it was 42 miles. And what we're trying to do here is to find the speed of the boat in still water. So where we were talking about adding the boat speed and the speed of the current, we're subtracting the speed of the current. The boat speed, we're going to make that x. So for upstream, we're going to have, for our rate, we're going to have x minus the speed of the current, which the problem tells us is 5 miles per hour. For downstream, we're going to have x plus 5. And then we don't know anything about the time except that the two times are the same. So again, let's take our formula, d equals rt, and solve for t, which gives us d over r. That means we can fill in these boxes for the time by taking our distance and dividing by the rate. For this first one, we would have 22 over the quantity x minus 5. Second one, we would have 42 over the quantity x plus 5. And then we do know that the two parts of the trip are in the same amount of time. So that means that these two have to be equal to each other. That gives us our equation. We have 22 over x minus 5 is equal to 42 over x plus 5. Since we only have one rational expression on each side, we can cross multiply. So that gives us 22 times x plus 5 is equal to 42 times x minus 5. If we distribute our 22 on the left side, we get 22x, and 22 times 5 is 110. Then on the right side, we have 42x minus 42 times 5, which is 210. Now if we subtract 42x from both sides, then on the left side we have negative 20x plus 110 is equal to negative 210. Then if we subtract 110 from both sides, that gives us negative 20x is equal to negative 320. Now we can divide both sides by negative 20. And the negatives cancel each other out here. If we divide by 320 by 20, we get 16. Now let's check our answer with our original equation. We have 22 over 16 minus 5 equals 42 over 16 plus 5. It gives us 22 over 11 on the left side and 42 over 21 on the right side. 22 divided by 11 is 2. 42 divided by 21 is also 2, so that checks. That means that the answer to our question, which was the speed of the boat in still water, is 16, and since that's a speed, we're dealing with miles and hours. That means it's in miles per hour. Our final answer is that the speed of the boat in still water is 16 miles per hour.